free training provided by the HVAC School podcast is made possible because of the generous support from our sponsors, Testo, Rector Seal, and Carrier. All right, so if you're anything like me, you used to have to work with line covers that were made of metal. And I'm not the best with sheet metal, okay? I'm in Florida. I've never done a lot of sheet metal work, and I can never get a metal line cover to look decent. And then when you had to paint it, getting the paint to stick was always a challenge because, it's metal. But then out came these different line cover products. And one of the products that I really like is the Rector Seal Slim Duct product. I think it's probably the best looking line cover on the market, and it comes in different sizes and has all the fittings. But also Rector Seal makes another product called Fortress, which is a line cover product. It actually comes in a kit, and so it has smaller sections. I think they're 4-foot sections that come in a box and different fittings. And it's a really nice value option if you need to do a line cover job. If you have a quick line cover job you need to do, you can actually keep one of those kits on your service van, which is really nice. So for all of your line cover needs, you can trust Rector Seal with both the Slim Duct and the Fortress products.
Meet Zoomlock, the 10-second flame-free refrigerant fitting from Parker. Reduce labor costs by 60% with no brazing, no flame, and no fire spotter. Discover how Zoomlock can help you be more efficient and productive. Visit Zoomlock.com for more information.
And now the man who thought dad jokes were funny before it was cool. Wait, it's still not cool? Brian Orr.
Hello, ladies and gentlemen. Thank you for joining me on this fine day for the HVAC School podcast, the podcast that reminds you of things that you might have forgotten, or maybe some things that you forgot to know in the first place. And today's podcast, today's episode, today's show, if you will, or even if you won't, is all about some electrical basics that you may have missed. And these are things that actually aren't taught in a lot of HVAC textbooks. These are things that are much more electrical sort of theory, but the things that have served me well. For those of you who don't know, I started off as an electrician's apprentice. My father and my uncle were both master electricians. My father was an electrician by trade. That's really what he did early in his career, and then eventually grew into running a construction company, but he still carries with him a lot of that interest in electricity and electrical theory. And as it turns out, I also have someone who's become a good friend of mine. Mike Holt is probably one of the world's most recognized electrical trainers, and he lives in the same town with me. And I've had an opportunity to listen to him in person many times, and he has a lot of great videos for free on YouTube, which you can find by looking up Mike Holt. So I have an interest in electrical diagnosis, electrical theory that goes beyond HVAC, admittedly, and I actually get some flack for that sometimes when I talk about some of this stuff. It's kind of like, what does that have to do with air conditioning? And I get that some of these topics aren't like the type of thing that you take and you immediately apply, but I'm going to do a little series on electrical diagnosis. And today's episode is on some basics, but then I'm going to show you some ways to apply that. Specifically, one of the most requested things I get is low voltage diagnosis. And low voltage diagnosis is an extremely big topic, and it varies a lot based on the type of equipment that you're working on. But I'm going to focus on some basics for residential, like commercial low voltage diagnosis in a future episode, but not today. It'll probably be the next one that I do. But today I want to talk about some of the core things that if new technicians, if they get them wrong, if they don't think straight about them, then they're going to have a hard time getting their mind wrapped around how to diagnose problems. And what I find with a lot of technicians is that because electrical diagnosis is such a ambiguous, sort of mystical thing, they end up just doing what they're told and never really understanding why they're doing what they're doing. And so I want to start with a few basic things, and then I want to talk about a couple terms and ideas that technicians often get confused. So the first thing is understanding what's required for electrons to move. Because really when we talk about applied electricity or applied electrical theory, what we're talking about is moving electrons around. We're moving them, and in that process we are doing work with those electrons as we're moving them around. So what's required for electrons to move? Well, what's required is a difference in charges, and that's specific to electrical. So in electricity, we create a difference in charges, and then we can get electrons to move. But more generally speaking, I like to say it's a difference in energy states. And you can kind of tie this back to a lot of things that we do observe. In HVAC, we always say hot goes to cold. That's a term that's been used for generations, maybe centuries. People have said hot goes to cold. And that's just a simplistic way of describing how energy tends towards equilibrium. Nature doesn't like an imbalance. So when there's a difference in energy states and those two states are allowed to interact with each other, they tend towards equilibrium. They tend towards stasis, towards a stable state from an unstable state, from a differential state. And so there's a lot of different things you can point to. If you think of a hill, I always draw a thing on the board where I show a guy pushing a boulder down a hill. And we know just from our experience that if you take a boulder and it's high on a hill and you push it down, it's going to fall. That's because of differential gravity states. You have a lower point and a higher point, and so gravity is going to draw that ball down from that higher state that's opposing gravity. So when you think about the laws of conservation of energy, you can't create energy. Energy isn't created. It can change from a more organized, usable state to a disorganized or unusable state, but what you put in is what you get out, basically. And so if you rolled a ball up a hill in order to get it to the top of that hill, and so the argument would be, well, what if it was always there? Well, okay. I mean, again, nothing was always there. It took energy to oppose gravity to get that ball or that boulder to the top of the mountain. And so now it's at that higher energy state, and now it's going to tend to roll down the other side because there's a differential in energy states between being higher in altitude and lower in altitude. And so you think about it with heat and temperature, hot goes to cold. You think of it with gravity. You can think of it in terms of another really common thing I'll talk about is water. Water we use a lot when we're talking about electrical theory. But if you think of water in a pipe that's closed off, so it's not flowing, but it's got, say, 30 psi of pressure in that pipe, it's got a 30 psi higher energy state than atmospheric pressure. So the truth is that 30 psi G that we measure in that pipe is actually 14.7 psi is atmospheric, so 14.7 times 30 would be 44.7. Is the actual pressure inside that pipe compared to the 14.7 atmospheric outside of it. And so there's 30 psi differential in energy between the pressure that's inside that pipe contained and outside. And of course, when you open the faucet, the water comes out because there's a difference in energy states. All that to say that in order to move electrons, in order to get electricity to move, it's the same as getting anything else to move. In order to get something to move, you have to have a difference in energy states. And so in the case of electricity, that difference is what we call a difference in charges. And so when you have something like a battery or a transformer, what you're really doing, you're not creating energy, you're not creating electrons, you're just creating an imbalance. So you can create an imbalance. That is something we can do. We can't create energy, but we can create an imbalance in energy to where we have a negative and a positive side on a battery, say, or two sides of a output on a transformer, secondary on a transformer. So if you think of a 24-volt transformer, a common misconception is that on a 24-volt alternating current transformer, that electrons go out one side and come in the other side. But we know that in reality, what's happening is it's constantly changing from positive, negative to positive because it's alternating current. That's sort of the definition of alternating current, right? But what is established is that there is always a differential. There's actually one point that there is no differential at the center when it hits the center of the sine wave, which we're going to talk more about sine wave here in a second. So that way there's always this differential. And it's always changing, but there's always a differential between these 2 points on the secondary of the transformer. So if you imagine looking at the secondary of a transformer and you've got a green wire and you've got your red wire, that's kind of the standard color code. A lot of people think, well, the green is ground. Well, in general, most secondaries on most transformers are ungrounded, meaning that they're completely isolated from ground altogether, and so there really is no ground and there's no hot. If you took one and touched it to metal, it wouldn't short, and if you took the other and touched it to metal, it wouldn't short. It would only short if you touched both to metal. Because the truth is that secondary, there's just a difference in charges between those two. There's 24 volts differential in charges between those two secondary wires on that transformer. It's not that the power's not going back to ground. We're just, within that transformer, we're using inductance, we're using magnetism in order to create a differential in charges. So create an equilibrium that then we use in order to move something. And really, in the air conditioning business, that's the whole point of what we're really doing, right? We're creating an equilibrium. We're creating an imbalance So that way there is not equilibrium that then tends to want to maintain equilibrium. So we take something that if you have an air conditioner and it's off, right, the refrigerant inside that unit will achieve a stasis. It will achieve a equilibrium between the outdoor temperature, indoor temperature. The refrigerant inside the outdoor unit will be the same temperature as the outdoor. Everything will just establish kind of this, it will just sort of settle down and everything will become the same temperature and pressure, right? But then as soon as we turn that unit on, then we create an evaporator coil that's colder, has a lower temperature than the indoor air. Now we start to move heat around, right? We create this lower temperature on that evaporator coil that then creates this natural inequity. Nature wants everything to be the same, and we create this lower temperature so that way heat comes out of the inside and goes into that evaporator coil. But that's the same thing that we're doing when we work with electricity, is we are creating an inequity. We're creating a separation between charges so that that way we can move electrons and then use them to do some work. And I know I may be killing this, but this is a very critical thing, because this is what happens when technicians will, new technicians especially, they'll use language like, I've got voltage at my contactor, or they'll say, I've got power at the unit. Well, that's super ineffective speech. And it's not just, a lot of people will say, well, you're just mincing words here. It's just language. No, I think there's a key misunderstanding here that a lot of technicians have, is that when you're measuring with a voltmeter, and this is proof positive by a lot of technicians using a non-contact voltage sensor. They use a non-contact voltage sensor as almost like a proxy for a voltmeter. And it's not effective, because what you want to do when you're testing with a voltmeter is you're testing for that difference in charges. And it matters completely where you're putting those two probes. So when a junior technician calls me and says, I have power at the bottom of my contactor, but nothing's working. This is a common type of way of speaking. I got power, but nothing's happening. Well, I want to know where you're putting the two probes. Because as you know, a lot of technicians will take a contactor for a condenser and they'll take one probe on the line side going into it, and they'll put it on one of the terminals, and then they'll take the other side and they'll put it to ground. And then they'll do the same thing on the other side, and they'll say, well, I got 120 on both sides. That means I have 240 going into the bottom of the contactor. And of course, we know single pole contactors, you can backfeed one of the sides, so you may have lost a leg. Often that'll happen in the disconnector and a breaker not making contact on one leg, but they'll swear up and down that they have 240 because they've got two legs of 120. But sure enough, when they take both of those meter leads and they read across the two bottom line in, L1 and L2 on the bottom of that contactor, they'll find that they have 0 volts, which means that you have no difference in charges. And when you have no difference in charges, you have no electrical work being done. So let's talk quickly about how most power is generated for what we use it for. Most electricity is generated. And it's most electricity that we work with is generated at a power plant, and it's generated in a rotating magnetic field. In almost every case, what's happening is you have something spinning. Let's say in the case of a nuclear power plant, I talk about this a lot because people think of nuclear power as being some like super magical thing, right? So you have plutonium or uranium highly enriched, and then that creates power in the nuclear power plant. But really all that uranium is doing in the nuclear power plant is it's just heating water, and then that water is boiling, and it's turning a steam turbine. And that steam turbine is turning some electrical conductors. We can say windings, but it's electrical conductors, and they're rotating within a magnetic field. That's what's happening, and then we're generating power into those electrical conductors. So we could be spinning the magnet, or we could be spinning the conductors one way or another, but we're generating power through magnetism in a rotating magnetic field. And so that creates what we call a sine wave. If you've ever seen a sine wave is just like these curves. So you'll see it looks like a mountain and then a valley and then a mountain and then a valley, and it goes across the screen. And I've realized that I've kind of taken for granted that people understand what that is. But here's a way to imagine that. A sine wave is nothing more than a circle that you've cut in half and then flipped. And so really what you're seeing is a circle on a timeline. So if you're looking from left to right on a sine wave, that's just showing the passing of time. So as you move from left to right, that's showing the passing of time. And if you were drawing a circle, you could draw a circle, it's just a circle, but then that wouldn't have a timeline. But if you draw a circle on a timeline, you get a sine wave. And so when you're generating power in this rotating magnetic field, it goes up and down, up and down, up and down, right? But it goes up and down in a circle. It's just constantly going back to where it came from. But in the case of displaying that in a sine wave, we want to show that with time so it looks like a wave going up and down. But realizing that it all actually starts in a circle may help you visualize what's really going on. So when you are measuring alternating current and you measure two 120 volt legs that are completely out of phase with one another, imagine them not so much as two separate points on a sine wave, a hill and a valley, the way that some people imagine it, and that's fine. But the reality is that one is at the top of the circle and one is at the bottom of the circle. And they're always opposed to each other, 180 degrees opposite from each other when you have a typical 240 volt residential single phase power input. And I've talked about this on the podcast before. I've written about it. It's actually really interesting how that's generated, because we'll say single phase power. And I always thought, well, why isn't it two-phase power, which two-phase power is a separate thing. But single-phase power, it is only one leg of the three-phase power coming from the power company. And then that second opposing sine wave is generated at the transformer at the street of your house, or, down on the ground or up there on the pole. That's where that second phase is, and it is created out of one phase. And it's just a matter of the direction that the windings are wrapped within the transformer. So you wrap one direction, it creates the sine wave in one direction, and you wrap the other direction, it creates an opposing sine wave in the other direction. And so that's how we get 240 at the pole. It's actually generated from one leg of distribution power coming in instead of being three-phase, whereas three-phase uses all three phases of distributed power coming straight from the power company, which I always think is interesting. And that has to do with how the transformers are set up and so on and so forth. But just remembering that it's generated in a circular magnetic field. And so the power that we get is good at generating another circular magnetic field on the other end, which is what we then use to spin motors and do the work that we want it to do, is that we have these opposing electrical fields, and they are opposing because there are a difference in charges. So something being, because I had a trainee ask me this just 2 mornings ago when I was doing a class about this, he said, which is always a good question, it's a good sign that he had this question. He said, so if you have 240, you have two legs 120, they're both at 120 volts, why do they read anything? Because there's no difference in charges, they're both 120 volts. But of course we know that in alternating current, 120 volts is a measurement to the center point. But from each other, one is 120 volts positive and another is 120 volts negative. The truth is that neither are actually 120 volts. They're constantly fluctuating up and down, and 120 volts is actually the RMS. If you're reading 120 volts with a meter, that's the root mean square, which is the average if it were to do the same work as direct current. The truth is that the peak voltage is actually higher than that, both on the positive and the negative side. But they're 180 degrees out of phase from each other, so if you measure them to neutral, they're 120 volts, you measure them to each other, that's where you get to 240 or 230, whatever your current voltage is in the area that you're working. But the point is that it's a good question, but if you don't think in terms of difference of charges, you just think of voltage as some sort of like ambiguous measurement that's just out there. It's just voltage, right? It's just power, and it comes from the ground. This is what I hear. In fact, I think I used to say that. I think I used to say early on, electricity is pulled in and out of the ground with alternating current or some such nonsense. But the truth is that at your transformer, at the road, you have an induced differential in charges, an induced potential difference, and you have that to work with, and it's constantly changing, and those two legs are 180 degrees out of phase from each other. They're 120 volts to ground, RMS, and 240 volts to each other because they're always completely out of phase. So if you think of one being at the top of the circle, the other's at the bottom. If the one is at the left, the other's at the right of the circle. They're always opposed from each other, which means that they're always going to be completely opposite from each other. You're always going to have that doubled voltage. Again, not at a given point, because we're not measuring at a given point. It's changing 60 cycles a second. So it's constantly changing, but they're always going to be opposed to each other, except that point when they meet right in the middle, which is a whole different thing.
The Testo 773, in addition to the features on the other meters in the Testo 770 series, includes real-time power measurements, watts, power factor, and Bluetooth. The Testo app can be used for remote viewing, monitoring, data logging, and creating reports. This powerful app allows you to create custom reports that include photos, data, and graphs that can be saved or sent via email. Find out more by going to testo.com or visiting truetechtools.com. As always, you can get a great discount by using the coupon code GETSCHOOLED at checkout.
So the final thing that I want to talk about here is the idea of neutral and ground. And I've talked about this, grounding versus bonding and neutral and ground and all that type of thing, but I think it's an important distinction to make. I just did this class recently, And a lot of guys get confused about this because one of the guys just kept coming back to, where does the power come from? Where does the electricity come from? And there's always this confusion about the role of ground in all of this. And the truth is that ground really has nothing to do with it. We use ground as a conductor for safety reasons, and ground becomes a conductor when you have transients, like big power surges, or when you have lightning strikes, localized lightning strikes that are near where you are. At that point, ground becomes a conductor because that's the place that the lightning is going to, right? Lightning is coming to the ground. So at that point, a lot of times it'll hit your house and you have to give it away to get to ground. That makes sense, right? But as far as the electrical systems that we're creating, we're just using ground. We're bonding the metal parts in a building. We're doing that just for safety. We're doing that so that way everything is connected together so that you don't have something that ends up being isolated, that shorts out, that then you touch, that then shocks you. The ground really has nothing to do with the operation of that transformer on the pole or that 24-volt 40 VA transformer that you have on your truck. Ground's really got nothing to do with that. The only thing ground has to do with it is what we make it. And it's just like in a car. You have a car battery that sits in your car, and it's 12 volts, right? It's 12 volts, and it's not connected to ground. It's got no reference to ground. You can take a meter, read across it, it's got 12 volts. Now you take that negative terminal and you connect it, you bond it to the chassis of your car, which now makes your entire car electrically the same as that negative terminal on your car. But you didn't have to do that. You just did that because that's what we do, and we do it for a lot of reasons, one of them being safety, but we make the car electrically the same as that negative terminal. But it didn't require being connected to the car for that battery to have 12 volts. And the same thing is true for your transformer at the road. Same thing is true for your electrical distribution system in the panel. And the same thing is true for a transformer. We don't have to connect anything to ground. We wouldn't have had to. We could isolate ground completely. You never connect anything to ground. You could do that. We choose to connect it to ground, and it's for a safety reason. It's so that way it can clear a fault. If there's a fault in a system where it's shorted out, we want it to trip a breaker. We want it to have an overamp condition, so that way it does trip a breaker, blow a fuse, that sort of thing. So that way it's not unsafe, right? Makes sense. But we get this sense sometimes that ground has something to do with it, that ground somehow creates electrons, or that's where we're pulling electrons from, and that's not the case. We're just creating a differential. In the same way that there's a differential on that battery, a difference of 12 volts, a difference in charges of 12 volts between the positive and negative, at our transformer in the street, we have a difference in charges from neutral, which is connected to the transformer. We have a difference of charges from neutral to each side of 120 volts, and between the two, we have a difference of charges of 240 volts. We're talking residential single-phase power here. That has nothing to do with ground. Now, the fact that we connect neutral to ground in our panels and everything, now all that does is that just makes the house electrically the same as neutral. We're making the house electrically the same as neutral, not making neutral electrically the same as the house. I mean, it's one and the same, but it's a really kind of important thing to get your head around. We're deciding what the electrical state is going to be of the metal parts in the house. We're deciding that because we're connecting it to neutral. And now neutral then becomes that center point where you have 120 volts from each leg to that central point. And everything that we do as far as connecting ground at that point and bringing it back to neutral is as a safety feature, so that way everything remains electrically the same, so that way we don't risk shocking ourselves, either through something that's shorted out or transients or static electricity or whatever. We're just making everything electrically the same. And so that's the reason why we do that. And when you think about bringing it back to the difference in charges, this is where I think technicians get confused, is they're always trying to come up with energy states in and of itself. Even when we say things like, my suction pressure is 70 psi. Well, your suction pressure is 70 psi G measured on the suction line. And in fact, it's in reference to the outside air. So it's psi G. 70 psi G is 70 pounds per square inch gauge. And that means that it's already calculated for the atmospheric pressure around you. So it's in reference to the atmospheric pressure around you. It's 70 psi in reference to the pressure around you. It's always in reference to something else. It could be in reference to, when we talk about temperature, sometimes we'll use absolute zero as our reference point. We'll say that instead of having a negative scale, we use the Rankine scale on the Fahrenheit side, and we start zero now at negative 460 degrees Fahrenheit. So we're going to reference that instead of what we would typically call Fahrenheit, because we want to have some sort of baseline. We want to compare to something. And so the something we're going to compare to now in the Rankine scale is going to be minus 460. It's going to be absolute zero. That's where we're going to start. And that's fine, but it's always in reference to something. When we look at any energy state, it's always in reference to something else. When we say something is high, we mean it's high in comparison to the Earth, because we're on the Earth, right? So that's the reference point we use. So we say that's high up there, that's high up in the sky. But if you're already on top of a mountain, that Earth is low, or another mountain that's a little lower is going to be lower than us. And so we're always talking in terms of two things that are in reference to each other. And that's never more important to us as technicians than when we're talking about electricity and the motion of electrons, which ultimately is what we use, what we harness to do work for us. And so I find myself constantly using a voltmeter and taking measurements between 2 points in order to diagnose things. An example of this is there's a lot of cases that I find myself taking a measurement between ground and neutral. And you would say, why would you take a measurement between ground and neutral? That's electrically the same. Well, exactly. They should be electrically the same. That doesn't mean they are electrically the same. Something I had to diagnose recently was a Danfoss variable frequency drive on a Sam's Club. I had to go out and diagnose it, and it was having all sorts of issues. I would measure the input voltage to this device, and it would read correctly. But what I found out is that the actual transformer that was producing the 24 volts that was feeding this was actually grounded improperly. So what should have been ground or a reference ground or a common on this variable frequency drive actually had potential to ground. And I found that out when I took what should have been a terminal that should have had the same potential as ground, and it accidentally touched ground and it arced out and actually blew a fuse. And so then I realized that the distribution transformer that they were using, this is a 480 volt configuration, they had wired it wrong. And so we actually had a significant differential between this common point that should have been the same as ground and ground, which was causing the issue. Again, that's sort of an abstract case there, but I found that actually because I saw an arc. But I found similar issues by measuring between what should be the same as ground and finding that there is actually a difference in charges there when there ought not be a difference in charges. And so you can do that on a house, for example. If you have a house where the ground and neutral aren't properly bonded, that can cause all sorts of dangerous conditions. And if you measure between ground and neutral on any building, and you find out that they have a difference in potential, so you're reading some voltage there, 10 volts, 20 volts, 30 volts, whatever it is, that's an unsafe condition. It shouldn't be that way. And so then you have to find what isn't bonded properly, what isn't connected properly, that's causing those 2 points to be electrically different. There to be a difference in charges there. That's on the negative, scary side. But on the positive side, when you're using a meter, that's when you can walk through a circuit and you can find where you have voltage potential and you don't, always recognizing that you're using both meter leads. It's never just 1 point. So you don't have power at the R terminal. That's not what you have. You have a difference in charges. You have 24 volts differential between the R terminal and the C terminal. So coming out of a transformer on the secondary, you don't have 24 volts at your transformer. You have 24 volts across the secondary, the two secondary leads of your transformer. That language seems really simple and stupid, but especially as you get into more and more complex controls, the two places that you're measuring are important, and one is just as important as the other. So it's using the term common for like this universal electrical phrase that just means everything, it gets more and more confusing the more complicated you get, because common can mean all kinds of different things. And so instead of using common or using the word ground or whatever, you're actually talking about a specific electrical point or two specific electrical points measured across each other, measured the differential between them, the actual electrical potential. And that's the best way to think about electrical energy, remembering that it's generated in an alternating current, at least, is generated in a rotating magnetic field with opposing points of differential. So it goes from positive to negative, negative to positive. The sine waves are opposed from each other. And understanding that words like neutral, ground, common can mean different things, and that none of this stuff is created. Well, the only thing we're creating is a difference in charges. We're not creating electrons. We're not creating energy. So I hope that was helpful for you today. Thank you for listening. I know these solo episodes can maybe get a little bit arduous at times. I've noticed that when I talk and I'm not talking to somebody else, I tend to talk really fast and sort of ramble on. So thank you for being patient with me. I have some episodes that are going to be coming up of me interviewing my staff, actually talking to them and doing some training with them. I've had a lot of you say that you liked those kind of original episodes. So I need to do that more often. Frankly, a lot of times I have these morning meetings and they just end up being hectic and a lot of questions, so I don't end up getting my recording equipment set up in time, but I'm going to try to do that more in the future. And I'm going to do an episode here, probably the next one, like I said, it's going to be on low voltage diagnosis and the way that I approach it. Some of it's actually going to be pretty controversial, but I hope to kind of allay some of your fears with low voltage diagnosis and how I approach it, because that's one area that has always come, I don't want to say naturally, but it's been an area that's always been a lot of interest to me. And so hopefully I can help you with some of that. But today was mostly theory. As always, you can find this podcast by going to hvacrschool.com, and you can find all of our other podcasts in the Blue Collar Roots Network by going to bluecollarroots.com. There's a lot of great podcasts there. A lot of them are air conditioning related, so I would encourage you to go check that out. So for my last birthday, my wife got me a mind reading calculator. She always gets me these really weird things, a mind reading calculator. I didn't really care for it too much, but it is the thought that counts. All right, thanks for listening. We'll see you next time on HVAC School.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.